Hello, my name is Greg Durling. I'm a rising second year in the Chemistry and Biochemistry department. My project is the synthesis of ionic liquids for directional solvent extraction. During this presentation, we will discuss the definition of ionic liquids, what is directional solvent extraction, and lastly I will walk us through synthesizing a precursor for an ionic liquid. Substances that consist solely of ions and have a melting point below 100 degrees centigrade are defined as ionic liquids. With seemingly endless variations of cation and anion combinations, this class of compounds constitutes a wide array of physical and chemical properties. Of these, we are most interested in thermoresponsive phase separation in aqueous solutions. The separation of a homogeneous liquid mixture into two immiscible liquids as a function of temperature has the potential to substantially mitigate the energy penalty associated with a broad spectrum of industrial processes involving separation, drying, and distillation. Thus, thermoresponsive ionic liquids exhibiting lower critical solution temperature and/or upper critical solution temperature behavior have emerged as conceptual alternatives to existing approaches in designing more energy-efficient phase change-based systems. World water supply is struggling to meet demand, and production of fresh water from the oceans could alleviate this almost indefinitely. Currently, the two major methods for desalinating seawater are distillation and reverse osmosis, each having its own set of drawbacks. Directional solvent extraction offers an alternative low-energy approach. The setup in a thermoresponsive ionic liquid-based directional solvent extraction system would look something like this. Initially, the brine would mix with the ionic liquid. Then upon heating, the ionic liquid draws water from the saline solution, yielding concentrated brine represented by Mx. This concentrated brine is then separated from the aqueous ionic liquid solution. A reduction of temperature then leads to a decreased solubility of the water in the ionic liquid, resulting in dissolution, and finally the fresh water is separated from the ionic liquid, and the ionic liquid is recycled for subsequent process turnover of the directional solvent extraction cycle. So, as the synthetic chemist in the collaboration, it is my job to make these ionic liquids, and as such I'm going to walk you through synthesizing a precursor to one of these fluids. First, all reactions begin with a planning phase. Typically, we search the literature to see if there is a known protocol for a specific transformation. Here, the goal is to install a methyl group on a nitrogen of pyrazole, as seen in the top of the picture on the right. This reaction is classified as an alkylation and is standard for the practicing organic chemist. Next, we do the stoichiometric calculations to know how much of the required reagents are needed before heading into the lab. Once in the lab, we need to prepare our equipment. Luckily, the only thing that is really needed for this reaction is a flame-dried round-bottom flask. Drying the flask in this way helps to limit the amount of water in the reaction, which can sometimes cause issues. It is now time to measure out the reagents and solvent and add them to the flask along with a magnetic stir bar. Here we have terbutoxide, the organic base, pyrazole, the substrate, 18 crown 6, which speeds up the reaction, and diethyl ether, which is a solvent. Next, we add our electrophile or alkylating agent. We do this while the flask is in an ice water bath. Iodomethane is a fairly hot electrophile, and keeping it cool helps control the exothermic release that occurs when this reagent reacts. The balloon in the picture is filled with argon gas, which provides an inert blanket over the reaction mixture, helping to keep it air-free. It is important to have an educated guess as to what is going to happen in the reaction vessel. Here, terbutoxide plucks a proton off pyrazole, giving pyrazole a negative charge and generating terbutanol. The deprotonated pyrazole then acts as a nucleophile and attacks iodomethane, displacing the iodide and affording the desired N-methylated pyrazole. Notice that 18 crown 6 ether sequesters the potassium ion. This likely increases the nucleophilicity of the pyrazole anion by keeping the positively charged potassium from interfering during nucleophilic attack. After 48 hours, a quick filtration is performed to remove the excess organic base. The filtrate is then purified via distillation. Distillation is used in this instance because methylpyrazole has a fairly low molecular weight, which makes it relatively volatile, so the temperature needs to be set just right in order to remove the solvent and unwanted byproducts. When doing a distillation, a slow drip like this is ideal. So that is it. We made methylpyrazole, the yellow substance shown in the flask. This precursor can go on to be used in the synthesis of a variety of different ionic liquids, including 1-ethyl-2-methylpyrazolium bisulfamide, shown on the right. And lastly, I'd like to give a special thanks to Dr. Brandon Ashfeld for getting me interested in ionic liquids, Eva Galati for teaching me all about the project, and the ND Water Fellowship for helping to fund my summer research and aid in my professional development.